All right, now we've gone through the basics of the TS diagram, and it's time to put our newfound knowledge into use. We're going to go around the cycle, the geothermal power system, right? And we're going to follow the fluid that we harvest from underground and follow its path around the various components. And we're going to see how it changes in terms of its mass flow rate, its pressure, its temperature, and its phase. We need all those things to calculate the amount of power we can generate from the system. I will do this in parallel. I will show you how the path that's followed here, how it looks on the TS diagram. But before we start with that, let's identify the components that we have. And I'm also going to label them in terms of numbers. Now, if you remember, here we have our production reservoir, right? Production reservoir. And this is where we start our analysis. We have fluid in here that will flow up the well. So this is our well until it reaches the surface, where we've installed a wellhead. Now, if you remember, as we mentioned in class, the wellhead is a valve, and it controls the flow of the pressurized fluid that's coming up the well. Now, what connects the valve with the next component are pipe segments. So this is surface pipes. Surface pipes. Connected to the valve with the surface pipes, we have our main, the first of our main components on the top side of the cycle, and that is our separator. And now, remember in class we talked about the different types of power generation systems that we have, and we said that if we have a separator, then our systems actually is a flash steam power plant. You've seen a different version of this diagram that was a little bit more graphical. This is a line diagram, and we use that as engineers to analyze a system and its flow. Going past the separator, we have the turbine. The turbine is connected to a generator. Following along, this is a condenser. That's connected to a cooling tower. This is a pump. Here we have two more valves. Okay, so those two are valves. Down here, to complete the circle, we have our injection or re-injection reservoir. Right, okay, so what do all these components do? Well, the well is, you can imagine, as a very, very long pipe, and it just creates a pathway for the fluids to flow from deep underground all the way up to the surface. The wellhead, as I said, is a valve. These fluids are pressurized, great pressures actually, so we need a valve to be able to control the flow. Now, the surface pipes connect the various components together. So we have surface pipes. If I were to put that, turn that into a star, that would be surface pipe. That segment would also be surface pipe. This one as well. This. This. And this. Why have I noted them? Well, it's important because for the purposes of this analysis, we can safely assume they do not exist. What does that mean? That if you know what the conditions of your fluid, the phase, its pressure, its temperature are at this point, you can assume very safely that it will be exactly the same at this point, right? First component here that we see on the top side past the wellhead is the separator. The job of the separator, unsurprisingly, is to separate. You have two-phase mixture coming in on the inlet, and if you see a separator, you can safely assume you have a two-phase mixture. You will have fluid in liquid form accumulating at the bottom, and you have vapor collecting at the top. As we said, we have a pipe that allows the steam to be directed to the steam turbine, and we have another pipe that collects and directs the liquid condensate out of the separator. All right, let me use some colors. Colors are good, right? Colors are always good. And let's just take this one step at a time. So we are down here. This is a production reservoir. What do I know while I'm down here? If you look at and I'm going to use the example we used in the lab for the purpose of this analysis. We know our m dot. Oh, and I'm going to call this point 1. So I know m dot 1. I know my pressure at 1, which will be actually pressure of the reservoir. And I also know my enthalpy at 1. And that's an important one, okay? Point 2, I will set at the top, the very top of the wellhead. But before I get there, what do I have? I have the well, and the fluid is flowing up the well. There's a number of things I can assume safely for the purpose of this analysis as my fluid is flowing up the well. This flow will be at constant enthalpy. That's the important thing, okay? So delta H is equal to 0. I also assume that I have no losses in the mass flow. So this is well insulated, and we have delta M dot is also equal to 0. But I will have pressure and temperature dropping as my flow flows up, as my fluid flows up the well. Wellhead, that's a valve. I have a valve. The main thing that applies in terms of assumptions, if this is the inlet and this is the exit, is that H at the inlet will be almost equal to H at the exit. At the inlet, I will typically have a large P, and at the exit, my pressure will expand and I will have a smaller P. Okay, so my pressure will drop. Similarly, I will also have a small drop in temperature, although that's more negligible. So what does that mean? So I have my enthalpy at the production reservoir. I'm flowing up the well. The enthalpy doesn't change because we have isenthalpic flow, which means that the enthalpy right underneath the valve will also be equal to H1. And based on the assumption that we stated here, the enthalpy at 2 will of course also be at H1. So H2 is equal to H1. As I'm assuming that the surface pipes have no effect on the flow, and let me be more specific about that. That means that delta H will be equal to 0, delta M dot will be equal to 0, delta P, delta T will also be equal to 0. And the phase in the pipe line will be unchanged. Phase unchanged. That means that at point 3, which is the entrance to the separator, my enthalpy H3 will also be equal to H1. The next thing to consider is the pressure. The wellhead, we said it's a valve. What's a valve? If you remember, talking about this, we said that a valve is similar to an interface. It allows two components of the same system that have different pressure to communicate with each other. This usually happens within the premises of a pressure drop, right? So I have large pressure down here and a smaller pressure here. If I assume that I have no drop in pressure on this side of the loop, then the pressure at 2, P2, which will be different than whatever pressure I have up here, will actually be defined by the pressure at 3, and that is equal to the operating pressure of the separator, P sep. So P2 is actually equal to P of the separator. Now the operating pressure of the separator is a design condition. You go to Separators R Us and you pick up a separator that operates at 7 bar. If you have more money, you will pick one that operates at 10 bar and so on. The next thing I want to look at for this particular part of the loop is the m dot. The m dot here is m dot 1. As I'm assuming I have no changes flowing through the well, and I have no changes as I'm flowing through my pipes. I also have no changes as I'm flowing through my valve. So we're going to have a delta m dot here also equal to 0. Then my m dot 1 will be equal to m dot 2. So m dot 2 is equal to m dot 1. And that will actually be equal to m dot 3 as well. So what am I missing? I know my enthalpy. I know mass flow rate. As I said, P3, sorry, I forgot to write it down, is equal to P separator. Okay. And also P2 equal to P separator. So I know mass flow rate, enthalpy, pressure. Let's take a look at the phase. That's the last thing we're interested in. Right. So down here, and this is given as an assumption in your example, the one that we're working at, I have pressurized liquid. So the pressure in the formation that's hosting the geothermal fluid is high enough to keep it at a liquid state. But what's going on? I am flowing up the well. Right? I'm going up the well. What happens to my pressure? It's dropping. What actually happens is that it comes to a point where it drops and it can no longer sustain that pressurized liquid phase. That point, let's just assume that it's somewhere in here, right? That point, you're going to get the formation of what? Do you guys remember? Hand on?
No.
You're going to see bubbles starting to form inside your well, right? What do we call that point? Anton? We call that point the flash point. Why? Because flashing occurs.